Okay, everyone, thanks for coming for today's little presentations. So I'll be talking about purrr, this particular package. Purrr. If you look at tidyverse, tidyverse.org, you'll see that purrr is one of these like frontline package for tidyverse. In fact, if you download the package tidyverse and if you load library tidyverse, these are the 6 package that is gonna automatically load into your R environment. And one of them is purrr. We know the power of like dplyr. ggplot really useful. Tidier, I think if you have come to one of our presentations with Sean, you would know tidyr well enough. Typo is kind of is very useful as well. It's kind of form the back end of some of these dplyr and tidier, and then you have reader that maybe one day we'll talk about it. But today we'll talk about purrr. It's a super useful, well, at least in my opinion, and I have only been using purrr for maybe the past like 4 months or something like that. Package. If we read a little bit of an overview, it kind of says something about functional programming. Basically, it's this like a concept to get us away from some of the very basic programming, like especially replacing many for loops. And so today I'm just gonna show you some of the purrr, like the map functions. Basically, all about purrr is the map function here, and how we use it to sort of reduce our for loops in our codes. All right, so again, if you haven't installed this package called Gapminder and tidyverse, you can install it now, and then I won't even load it right now. So I'm going through a few cases where I feel like we would definitely find purrr very useful, and then maybe we can talk about more. So there are more functions than just map functions in purrr, but I'm going through the very basic functions in purrr. So suppose we want to test this idea that, so if you have populations of 10,000 or 100,000 or something like that, and you know, one of the basic idea of statistics is that if you sample more people, your mean is gonna be very similar to population mean. Whereas if you have less sample, if you sample only 5% out of these 100,000 people, the mean that you get from these samples may be very different from the population mean. So suppose we want to have this idea, we want to test this idea. So first of all, over here, I create a bunch of fake population data. So for this, so there's like a, say, assuming that there's a population of 10,000, the true mean is 0, true standard deviation is 1. This is our like a true data. So it's called pop populations here. So suppose to test this idea, I do these simulations. First, I sample only 1 person out of this population. Then I sample 2% out of this population, 3%, 4%, up to 1,000%. So my N, my sample size, goes from 1, 2, 3, 4, 5, 6 to 1,000. All right, so, well, first of all, we can try to use the for loop way of doing things. So I create an object called M1. It's basically to store all the means. So basically the idea is first we sample 1% out of the population, record the mean of this 1% sample, and then put it in this particular vector called M1. All right, so I first create M1 vectors that has like 1,000 spaces. All of them are MAs right now. Again, if you went through, I think, presentations by Michael 2 weeks ago, you will know that like creating an empty vectors that has already, you know, a specified length is always better than you know, like appending them using the for loops, because that saves a lot of computational power and time. So using the for loop, I say that I have the iterator. Iterator is I. I say that for I in 1 to 1,000. So from 1, 2, 3, 4, the iterators just keep adding. Okay, so first from the population, I sample I person out of this population, and then I call it X. Okay, then I say, and then I calculate the mean of the sample populations, and then I assign it to the ith positions of the M1 vector. So if you run this few lines of code, you'll see that now M1 is full of numbers. If you type M1 here, you'll see that there's like a whole bunch of numbers here. So each of them is like the sample mean of that particular sample size. So if you plot it, just a simple plot like this, you will see that, well, it's kind of true that the sample mean sort of slowly converge to 0, which is our true mean. All right? Now, this requires for loop. So the question here is, well, what if I have for loop phobia, or, you know, there are people who are actually afraid of using for loops and things like that. So then we have, oh, where's my cheat sheet? I'm sorry. Okay, so yeah, let's try the second way, which is the purrr way. And I'm trying to sell you the idea that using purrr is easier to read. It still requires a little bit of like a thinking on how exactly to construct this purrr functions, a map function to do your job. But it should be cleaner and easier to do so. All right, so first I would have to load my, import my library tidyverse. So again, if you run import the library, you can see that these are the bunch of packages that is like by default loaded into your R environment. And one of them is purrr. All right, so purrr is always about this function called map. If you read the help file, ooh, hey, come on, wake up. Sorry. Okay, my RStudio doesn't like me. All right, let's have another RStudio. RStudio hates me.
But I haven't checked the output to help. No, well, I've had the issue where I have like a separate output and I move the screen too quick when I'm trying to move the window around, it actually crashes.
All right.
If you try to do something too quick in there, it'll crash.
Yeah.
How I can prove this around.
This is not fun. Not fun, not fun, not fun, not fun, not fun. Okay. Back. Uh-huh. Library, tidyverse. Now, since it's throwing tantrum at me, I'll look at this help file because this is also a help file. So the title would say everything about it. So it's basically to apply a function to each element of a vector. In this case, vector, if you look at down here, is a list of atomic vector. So you can supply a vector or a list into these functions, and we will apply the functions to every single element of that particular vector or that particular list. And so you can see that the second argument is actually a function or a formula or an atomic vector. So back to what we have here, we have n. N is no, because n is not declared yet. Okay, we have everything up to here. Okay, so here we have n. N is a vector from 1 to 1000. So if we can apply a function onto each element of this n, we can do a very similar job to what we have up there. How can we do it? We can try this. So map, the first argument of map is n, is a vector or list that you want to apply a function onto. And that is where the second argument that we need to kind of understand what it means. All right. I want to apply a function. I would have to use a tilde. A tilde would indicate that I want to apply a function rather than something else onto the vectors that we have here. And if we look up here, what we want to use n for is to do sampling, right? So we would come down here. We would do the very similar thing, sample, pop, and where does the number come from? The number comes from the n. And if you look at the help file, it would say the first argument is called .x, which is where we use here, .x. So basically, this would mean that for each element of n, apply the function sample pop, and using the elements of n, drop it in .x, these particular positions. Okay. And I call the new output M2. All right. So if you look at M2, now you see that for it's actually a list. So the output of a map is a list, as you can see on the console. The first output has only one value. The first element of the list has only one value. The second element of the list has 2 values, and then 3 value, 4 value, 5 value, 6. And if you look at the environment panel, you can see that M2 is now a large list. And if you expand it, well, it did say that large list of 1000 elements. So what map does is, it creates this list. For the first element of this list, it does sample pop and put in the first value of n, which is 1. And then it goes to the second element of the list, and it does supply the results of sample pop, second element of n, which is 2, and then 3, and then 4, and then 5 to 1000. Any question? Make sense? All right, so now, but what I mean, I don't want each of these sample value, right? What I want is the mean of them. So I can pipe this into another map function. Now, the output of the first map function is a list. And we put a list into another map function, which works, right? Because just now we see that map takes in both vector and list.
You can't get the sample with the mean. That first one, you could go.
Oh, you could. You could. Yeah.
So you just want to show how you.
Yeah, I just want to show like slowly extending it forward. Yeah. So now we have a map. Now we want to take the mean of every single element, right? For the first element, we take a mean, which is the same as like 0.0699 something. And then the mean of the second element, the mean of the third element, the mean of the fourth element, and so on and so forth. So for each of the elements in this list, take the mean. So we use mean.x, right? For each of the elements of the list of the previous output, we take the mean of it. And we mentioned that we want to take the mean of .x, which is the object in front. When we do this, and then again, you look at what M2 becomes. Now M2 becomes just a single number for each of these 1,000 elements. All right. So yeah.
I think you already explained it about x. We don't need to define it. We need to define anywhere we can just use it, right?
Right. Yeah. .x means refer to the object previous in this position. But when you pipe it, the output of these things is automatically occupying the first arguments of map. So you don't need to type it out anymore.
I mean, even you have x before for the first record, but even I didn't run it, I still get a result.
Oh yeah, because .x is referred to this object.
Okay.
.x is referred to the object, the argument in front, not the same as the x that we have just now.
Okay.
Yeah, .x is different from x. Yeah, .x only live in this world, or only live in the map functions. It doesn't live anywhere else. Yeah.
That's because the map function has two arguments: .x, which is for the vector of the list that you're working on, and .f, which is the function that you want to apply to that list.
A standard argument of the first argument of map is .x. The second argument of map is .f. All right. So, well, now we have a list of 1,000 value. It's not quite the same as what we have up there, which is a vector. So if you look at M1, M1 is a vector, right? M1 is a vector of 1,000. And now our M2 is a list of 1,000. It's not a vector of 1,000. You cannot plot M2 like what we have in M1. So it will say that X is a list, blah, 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 but does not have component X and Y. So we need to somehow transform our list into a vector. Turns out purrr does a pretty good job about this. So if you look at here, apart from map, you see that there's map underscore LGL, map underscore CHR, map underscore int map underscore dbl. So what it means is, instead of just, so the base map function gives you a list. Map underscore lgl gives you a logical vector. Map underscore chr gives you a character vector, integer vector, double vector. Double is a form of like it's a form of numeric numbers. It's just that double, I think it means using 8 bits or 16 bits to store your complicated numbers. So that's what we are going to use here. So if we use map underscore, in this case, because our number is of what we call floating point number with a lot of like numbers after the dot, after the decimal point, so we use double, map double. If we run this again, you can see that M2 in your environment panel now is a numeric vector of 1 to 1,000 elements. All right, and then we can use plot function. We can plot the M2, and we have type equals to line. And you see that you have a very similar patterns of M1, which is that as your sample size increase to 1,000, your sample mean is kind of like going to the to 0, which is our population mean in this case. All right, so that will be my first little case of like how we can use map function in R using purrr. Any questions?
Got an error when I tried to plot the bar. It showed that figure margin is too large.
Oh, wow. Figure margin too large. You might have to change the graphic parameters.
It did look like that first doc that was created was pretty large. It was almost 4 megabytes.
Sorry?
When you first did the map, it without applying the converting it.
Right. Right. 4 megabytes.
Size there was 3.9 megabytes.
Yeah.
So that was
Huge.
Yeah, I mean, you're getting some size there. I mean, you're not outrunning your capacity.
Yeah.
It's fairly fast.
Something will happen if so when you increase the number of like n, something bad will happen. But yeah, basically I'm trying to sell you the idea of, well, method 1, you have, you know, a little bit more than 5 lines of code where you can actually condense it down to you know, 2 lines of codes and doing the same things that you want to do. And in this case, if you know how to read this, it's actually pretty clear. Like first, I do a sampling of the populations, from 1 to 1,000 times, and then you take the mean out of it, and eventually you have another line of code that says you want to plot it. So that's the whole idea of like trying to not use for loop in this case, and get some pretty neat code and relatively easy to implement, I guess. Yeah.
So the reason why you do the double in the second map is because you're taking in a list from the first
right.
map, and then that result will be the final evaluation.
Yeah, the reason I have a double here is because I want the output to be a double vector. A double is a floating point, so a double vector. So because remember, if we don't do this, our output is, our M2 is a list. The output is a list.
Right.
So map without anything, the output is always a list. So with something, with double, the output will become a vector. Or I think in Hadley Wickham's language, it's like they would die trying to convert it to a vector. Yeah, so yeah. Yeah. So it's like trying to use from the list, it's trying to convert it to a vector automatically. So you don't need to do anything else apart from mentioning about underscore DBL to say that you want the output to be a vector. Does it make sense?
Yeah.
Mm-hmm.
I was just asking why it was on the second map instead of the first one.
Oh yeah, because the first map, we still want to keep it as a list.
So
Yeah, because remember, our first set, so our first sets of argument cannot be a vector. If it's a vector, that means this. Okay, if we do this, it will be interesting. Well, result 2 is not a length 1 atomic vector. So why is that so? Because the first element has one value. The second argument, second element of the list has 2 values. The third elements of this list have 3 values, so on and so forth.
So it's expecting,
and they cannot be bind together.
It's expecting an input of a list or a vector of like 1.
Yeah, that's right. That's right. Yeah, that's why you cannot do a map double in the first argument. You have to do it in the second argument. All right.
Is performance equivalent between this and a for loop?
You sacrifice.
Map is slower.
Map is slower. Yeah. Yeah. You sacrifice. You do have some sacrifice there. Yeah. That's why I don't talk about it. Because I'm trying to sell it.
Did I ask that?
All right. So I mean, the whole idea of this exercise, we want to test if sample mean approaches population mean when the sample size increase. The same thing, same questions you can ask. The sample standard deviation or variance would also approach the population variance or standard deviation when our sample size increase. So is there a way for us to just test all of these things all together? You know, because just now we only look at the case of mean. Right now we are looking at both mean and standard deviation. Is it possible? So here is what we're gonna do. There's some coding problem here where it should be 1,000 because we are doing 1,000 instead of 10,000. Again, we look at the for loop way. For loop, again, is always a good practice to create a empty storage or empty container before your for loop. Then in the for loop, you just fill in the blank. So first step is we create a data frame. We state specifically what we want to store in this particular data frame. And then we run the for loop. Again, we do the same thing, right? We sample from the populations from 1 to 1,000 times. And then for each of these, like a sample, we store the informations of how many n we have. In this case, it's I. We store the informations of mean of the subsample, and we store the informations of standard deviation of the subsample. And so this is what this line is saying. All right, so now we have that, and we can use this to plot our line curves of this is how the sample size, sample mean changes along the gradients of sample size. And we can also look at the fact that the sample standard deviation actually approaches the population standard deviation. In this case, it's 1. And it looks pretty convincing in this case. All right, what about purrr? So we just now saw that we can use map function to create a vector using map underscore double. All right, turns out we can also use map functions to create data frame. And I realized maybe I need a cheat sheet. So all right. Okay, so let's do this together. First of all, yep. Oh, hi.
What happens if like an error dividing by 0? Does it still return everything? Or
I think the conventions of R, if you do a dividing by 0, is to give you
like if you're doing a function, you're doing the whole, you're doing math.
right.
Will it just say error and then just keep going? Or
That
will
is
it,
a good question.
kick you out?
Let's
It'll kick you out.
let's try this. Oh well, at least as far as I know, if it would just return an A for you.
Okay, because that's actually beneficial. The for loop just kicks you out.
Yeah, for loop just kicks you out basically.
Like if something doesn't convert.
Yeah. We'll look at situations where we actually get an A in this particular code. So just as what we did just now, right? Map, we first sample from the population, one at a time. Each element of n is being placed onto this function. Now we have the subsample. We have 1,000 subsamples. We want to look at both the mean and the standard deviation. Turns out we can use map underscore df to do that. All right. Map underscore df, as what we've seen just now, would be that it produces a data frame output for you. Now, what should go into this data frame? It should be a data frame. Okay, so that the map function can combine a lot of data frames into one data frame. So what's in here should be kind of like a data frame so that they can eventually be combined together. Oops. Now, what I could do here is I create a data frame. I say that mean should be equals to mean of dot x. Remember that dot x now is the subsample. So the first element will be subsample 1, second element will be subsample 2, so on and so forth. So dot x in this case, we are taking a mean of the subsamples. And then we want to know also the standard deviation. So standard deviation of the subsample too. All right. And well, of course, it's a data frame. I want to also know that how many subsample, what's the sample size for each of them. MapDF has this very cool arguments that you can put in to do that for you. It's got .id. Okay, maybe I should not show the .id first, and we can see what's the difference between one with .id and one without .id. So if we run M2, this line of code, if we look at the head, the first few lines of M2, you can see that the output is mean and standard deviation. And you can see that the first standard deviation is NA, because standard deviations of one sample doesn't exist. All right. So having an extra arguments of .id is pretty interesting. I call it .id of n. Right? And if you run this and you look at the data frame, now you have an extra column called n. And the extra column of n has the, well, basically the what's that? Sample sizes for each of that correspond to each of these row. Now you may ask, where does the standard n comes from? How does map underscore df function know what to populate, what to put into this particular new column that's called n? Turns out when we do this step, M2, when we look at this particular output, and if we do hate M2, you see that the first element is called 1, the second element is called 2, so on and so forth. So when it pipes into okay, when the output of this list, when this list get pipe into the map underscore df functions, the .id part would automatically fill in that particular column with the names of this list. In this case, there's no name for this list, so they will automatically just put 1, 2, 3, 4, 5, 6, 7, all the way down to 1,000. All right, and that's how you can create a data frame out of map functions.
So if you were doing instead of mapping over like a sequence of numbers, over say certain types of vectors or something like that, the data frame, when you did that .id, it wouldn't be 1, 2, 3, 4. It would be the names of the vectors.
Yeah, that's right. Yeah, we will have an example of that later. All right, and if you want to plot, just want to have a look of whether or not our theory is true, you can do that. And yeah, you can see that again, our sample standard deviation actually converges to population standard deviation, which is 1. All right, so in the next couple of examples, showing you using a data frame, using a data set that we have. So just now, so far, what we have been showing is some random numbers that we generated. All right. In this case, I'm using this library called getminder. So if you haven't installed it, you can install it. Otherwise, you can just import into your R environment. Now, getminder, as I've written here, is a data set with life expectancy, populations, and GDP per capita from 1952 to 2007 every 5 years. And it's a pretty good toy data set. Like you can play around with, you know, teaching, for example. Yeah, as you can see here, there's country, Afghanistan's, continents in Asia, from year 1952, 1957, all the way down to 2007, the life expectancies, the populations, and the GDP per capita. All right. So you look at this data set, you'll be like, well, maybe we are interested in building a model. We want to model life expectancies using some of the other variables that we have through this data set. So you have an idea, maybe I have 5 candidate model. In this case, first candidate is life expectancy is a function of populations. Second model is life expectancy is functions of GDP per capita. Third models is population and GDP per capita with an additive models in this case. And then fourth, you have a year and here. Fifth, you have year and also continent. So one thing that you can do is you create 5 variables called F1 to F5 with the respective formula. And then you can run the 5 models, M1 to M5, 5 times. And then you can look at a summary of 5 of them. So you do summary M1, summary M2, summary M3, summary M4, summary M5. All right. And then if, say, for example, you want to do model selections, you say which of the models is the best, you can actually use the function called AIC, and then you put in all 5 models object into it. And it will create a pretty neat table of the 5 models with the degree of freedoms of each of the models and the AIC of each of the models. In this case, it seems like the 5th model is pretty good, pretty solid, because like it has a lot lower, right? Yeah, lower AIC values, which is a criteria to choose the best model. So this is only 5 models. You can do 10 models, and then you will have 10 F10s, and then 10 F5, 10 M and 10 Ms, and then you have to rewrite these things summary M1 to M10 10 times, and then you have to do this 10 times as well. So it's pretty tedious. Of course, if you know how to use for loops and something like that, it helps a little bit better. But we are looking at how maybe we can use purrr to deal with this kind of problem. Now, what would the iterator goes to? In the map or in for loop, for example, what are the things that we want to change in each for loop? If we were to build a for loop out of this. What exactly is different for each of these models? The variables, or basically this is the formula. So the formula would change, right? So we say that, okay, can we create a vector of 5 formulas? Because we have F1 to F5, right? Can we create a vector of 5 variables? Let's see. Formulas. Now we create an empty vectors of formulas, and then we say that formulas, the first element of the vector, please be F1. All right, it would throw you an error. Okay, yeah, and the explanation is down here because vector doesn't work here because like the vectors is only available for numeric, character, logical, and I think that's all. So we have to use list instead of vector. So again, as I say, map function works with vectors and also list. And in fact, list is very extensively used in map. I think when I first learned map, I was actually using lists instead of like vectors. It's only later you discover that like, oh yeah, you can actually use vector as well. So we have to first create a list. A list of things that would change from one to the other. In this case, it's the formula that is changing. All right, so I can do list F1, F2, F3, F4, F5. Let's call it formulas. All right, so now I have a list of 5 formulas, as you can see here. Okay, the way you can tell that it's a list is because the output has double square brackets instead of single square bracket. All right, so now we want to apply something onto each of these lists, each elements of this list. So we map using formulas. That's the first argument. Okay. Secondly, we want to apply a function. And when you want to apply a function, chances are you have to use a tilde. As you can see up here, we use LM function to build this, to fit the model. So over here, we also use LM. We want to fit the model. So the first argument of the LM is a formula. We have a list of formulas in front. That's why we put a .x here. Oops. .x. And then the second argument is data, right? Data equals to getMinder. Now I would call this, let's see what I called it, mod. All right. So if you run this particular code, and if we do mod, you see that you have a list of 5 LM object here. Okay, this LM object is not very interesting. As you can see, there's like a formulas and then there's coefficients and that's about it. So maybe we want to look at the summary of these 5 objects. So we can pipe and say summary. I'm sorry. You have to map it. Remember, you want to apply the summary functions onto each elements of this list. So you do a summary. Oops. .x. Right? You want to put each of the model into the summary function. Okay. Now let's have a look at mod again. Yeah, well, you will see for each element of this list, it will be some output like this. First, it will say the call, which is quite useless here because it's .x. It has the residuals with the minimum, maximum, and the quantiles, and the coefficients, and the t-test of each of the variables. And the residual standard error, you have the r-square values and f-stats. And then repeat 5 times. This is still not quite what we want, because just now when we show AIC, we have DF, we have AIC. We don't really want to know everything else. Under this scenario, we don't really want to know everything else. We just want to know this, right? Can we do it here? Quite apparently we can do that, right? So let's try it out. Now, all right, I will still need the first one. So now I'm not interested in the summary. I'm interested in something else of this models. So first of all, I need to talk about a few functions for LM. First of all, DF residual. DF residual of a model, of a linear model, gives you the number of residual degree of freedom. All right, AIC of a model gives you the AIC of the model. And then I have also formula of a model. Gives you the formula of that particular model. Okay, with that, I can build a data frame that is like pretty informative. Now, I want my output to look something like this, right? Something like AIC, the tables that we did just now. So first of all, we need to have map to a DF. We want to build a data frame this time around. Again, when you do a map DF, most likely the output of whatever you do here should be a data frame. In this case, I just hardcore and go on and build a data frame in this particular code. Okay. The first argument, well, it's not very informative. M1, M2, M3, M4, M5. It's not very informative. So what we can do is we want to know the formula that correspond to each of these DF and AIC. Okay, what we can do is we say formula. So the first argument, the first column of the data frame that we built is called formula. The formula is gonna be formula of the dot x. Remember that each of these this list is a LM object. So when we do a formula of these things, it automatically gives us the formula of that particular linear model. And secondly, DF, okay? DF, we use the DF residual of the dot x. Then we want AIC, so we can do an AIC of the particular models, the LM object. And lastly, I just don't want it to behave strangely. I ask it that string X factor. No, yeah, something is wrong. Yeah. What might have been wrong? Something is wrong, but I'm not sure what. So let's just equals to F. Let's see if it works. Oh, okay. So turns out, so a formula object is not the same as character. So if you look at formulas, these things doesn't have a double quote on it. So it's not a character and it cannot be easily coerced. But there's a function called format that can change the formula object into a character object. All right. Coercing to character, coercing to character, coercing to character. Something tells me my string X factor is not working. Well, let's see what happened to my output. Okay. Anyone knows how to deal with this?
We're literally just creating on top.
So go to the comment.
Oh, strings as factor.
The tab auto doesn't work when you enter a new line, but if you do it after the comma, then you do the tab auto. So like if you would have done it after the comma on line, we can do the AIC.
Yeah, I think I was tabbing at some point after I typed the A there, like without the S. That's why it says there's nothing. But yeah, now it gives you a pretty neat table with each of the formulas of each of the models and the DF. Oh well, DF in this case, you can see that it's slightly different from the DF up there, but there's another function of another DF that might, oh well, no, not really. Maybe it's a, no. Yeah, you have to use the extracts in some other ways to do that, but it might be a little bit more trivial. Okay, any questions at this point? I'll just have another examples and then we can close this, if you bear with me. Now we have a new model. This time we only have one formula, one types of formula. But instead of applying to all countries in the whole sets of data of like thousands of entries, we are interested in applying the same model to each country. So in this case, it says one regression for each country. All right, so let's try to do this. Now, there's a very interesting function called split. All right, this function split is a base function. If I tell R what factors that I want to split so now I want to split the data frame into one data frame per country, because you want to run model on each country, right? So let's do this. Split dot country. Dot is basically a little bit of abusing the notations, but it basically means that take the getMinder and replace dot with getMinder with the previous arguments. If we do that, now my get by country, if we do head of get underscore by country variables, you can see that it's now a list. The first elements of the list has a name called Afghanistan, and the table only have the rows that contains country, where the country column is Afghanistan. The second element of the list is named as Albania, and it has this particular data frame stored in this particular elements of the list. So if we do get by country, if we use the original notations of double square bracket of 1, it will give you Afghanistan. Okay, and likewise, you can actually do get by country, say Zimbabwe, and it will give you the data frame concerning only Zimbabwe. Okay, so this looks like we can apply a function onto each of these, like a small data frame in this list. Now, map get by country, and then we can apply our linear models. Say, for example, we are interested in, oh yeah, you need a tilde because you are applying a function. Linear models of life expectancy according to, say, year. I forgot. It's the year. Okay, year in small letter. All right. And then I say that data is .x because the input is a data frame. So data is .x because get underscore by country is a list of data frame. Cool. What else do I need to know? All right, let's try running this. Oh, okay, save it to something first, okay? Mod by country, maybe. Model by country. So if you look at down here, model by country object is a large list of 142 elements. We can say, for example, look at a country-specific model. In this case, maybe Afghanistan. Oh, okay. Well, not very informative. You can do this, right? You can pipe into summary. Yeah. So now you have a details. Well, it's still a summary, but it's a detailed summary of the linear model that we fit using only the information from Afghanistan. Well, as you can see that, okay, say for example, in this case, it would mean that life expectancies of Afghanistan has been increasing over the years. The effect is very significant. It has an adjusted R-square of 0.9425, so it's a very good fit. It's a very good linear fit. Okay, say for example, now, well, it's very difficult to read. There are 146 models in this list. I'm not interested in any of them. I'm only interested in R-square value, for example. Unfortunately, there's no function called R-square that you can extract. Like just now, we have AIC, we have df.residual, we have formula that we can extract from the country. From the model. So we have to do some list magic. So first of all, we go to summary. Okay. So in this situation, we also applying a function called summary onto each element of this list. But I did not use any tilde. I did not have any parentheses behind the summary function. That's because you can choose to use this way to specify, I want to apply summary onto each of these objects in this list. It works the same as doing this. All right, both of them are equivalent. Now, as we did it just now, this would create a summary, a list of summaries in this case. That's not what we really want. What we want is the R-square value that is contained in the summary object. We can do it this way. We can do it what I would call the hacky way, which is like this, r dot square. All right, this means that take the R square object out of the summary object. Okay, if we do that, if we look at mod by country, if we just look at the first few, these are the R square value concerning each of the country. Okay. Another less hacky way of doing it, let me copy and paste this, is that we can specify from the summary of the linear model, take the R square value that is stored in this particular summary object. This only works, both of these codes only work if the summary object actually have a specific element that is called R dot square. Otherwise, it wouldn't work, right? But in both cases, it gives you the same thing. right? In both cases, it gives me the same thing. You realize that the first element now is named Afghanistan, second element is named Albania, third one is called Algeria, so on and so forth. What about, let's build a data frame with the country name on one column and r-square value on the second column. We would have to use DF, right? MapDF. And when you use MapDF, whatever is inside here should result in a data frame. Maybe we can call it, again, like what we have done just now, we just create a data frame out of these things. And then, well, I create a column called r-square. Ooh, spelling error. R-square is equals to .x, because all of those values, each of them are one value, but it's called r-square. It is an r-square value, and they are to be filled into these particular positions. Now, I need another column called country, because that's what we want. We want to have a country in one column and r-square value in the second column. It's a little bit difficult to do it within this framework, because what would you call .x now? Like, what if we were to do the country equals to, what should this be filled? We don't really know. Okay, and that is when the map_df functions comes in handy. There's a .id arguments that we talked about just now, right? If we do a .id equals to country, it will create a column of country and name each row after the name of the elements itself. And when we do this, and then again we look at the head of it, now we have two columns. First column is country with each of the countries, and then the r-square value that corresponds to each of these countries. All right. So, and I mean, for me, I've been using purrr for a few months, and I think a lot of usage for me is the two examples that you just saw. Like, if I have a number of different models and I want to apply to these sets of data, instead of using a for loop to create, to do it like 10 times and store them in a list, or store them in F1 to F10 and M1 to M10, I store them in a list, and I can manipulate the list using map functions. And in the second case, again, it's a very good use case for when you want to split your data into multiple parts, and then you want to apply some sort of like a complicated functions. This is a very good use case for using purrr. All right, I have some exercise. If you want to do it, if you feel like doing it, you can check it out. So basically, now I want to look at the, I think, mean life expectancies and mean GDP per capita for each of the region in each year, each of the sub-region in each year. So I have ANZ, which is Australia and New Zealand, Southeast Asia, where I come from, South Asia, and East Asia. So if you have four of these sub-regions that you are interested in, and you want to know the mean life expectancies of this sub-region, would you be able to use a map function to do it? It would be easy for each of to apply on each of them, right? With multiplier, you can easily do a filter and subset only the two countries, and then do a group by, and then or no, you don't even do a group by. You can do a summarize on that. But is it possible for us to apply a set of functions that does all these things on all four of these sub-regions that we are interested in? Just an exercise if you feel like doing it. Yeah. So that's the end of what I have to present. Yeah. Do you have any questions? Yeah.
Is there a way to use the dplyr method to select a particular list slot? So like if I want to take Australia out of the R-squared value list, is there a way to do that with the dplyr method?
Oh yeah, I mean, dplyr methods is totally incorporated into this. That's why they are part of the tidyverse family. As an example, I can show, say for example, I have a split over here. Okay, so this is by country. I did a split, right? I can also do this, select, map, sorry. Always map. When you have a list of objects, you always use map. Otherwise, you won't be able to do anything. So you can map, select. The first argument is a data argument. In this case, it doesn't carry forward from the pipe. So you have to do a .x here. Oh, wait, maybe not select. Maybe we're talking about filter here. Okay, year larger than 2000. Ooh. 2000. Okay, and if we run this, if we look at this head of this, you can see that only two years per country is being selected. Yeah, so it's totally incorporated.
You can also, if you are at some point mapping out to DataFrame, you can use dplyr functions in your sort of pipe as well. One thing that's been super useful for me, Ben's been helping me learn this tool, is I have some instances where I write my own functions that I want to apply over a bunch of data.
Right.
And you can use map with your own functions. You don't have to use this. That's been really useful for writing code that's pretty condensed and easy to follow what's next.
That's right.
Any other questions for Ben?
He posts it filled in one as well.
Sorry?
You post on the website, you post the one where everything's filled in as well.
Yeah, so he's got it on the GitHub account, and we'll post the link on the website.
Yeah. I mean, yeah, if you're interested in, we can go through the exercise later. All right, thank you very much. All right.
Okay, so we got 40 minutes or so to go around and help with